Hello, my name is Carmen Caprau. I work at California State University, Fresno. I would like to thank you for clicking on the link to watch this talk, and I hope you will enjoy it. And of course, I would like to thank the organizers of this seminar and for giving me the opportunity to speak. So thank you again, Micah, Robin, and Sujoy. You guys are doing a great job with this seminar. So today I want to talk to you about movie moves for singular link cobordisms in four-dimensional space. This is a work that actually I did a research for it in 2015. I had a lot of good time when I did that research. The corresponding paper, it is now published. It was published in 2016 in JKTR, and you can find it also on archive. I thought that I want to talk about this because it's pretty cool, at least in my opinion. And I haven't had a chance to give a long talk of it, only a shorter talk, 20, 25 minutes. And I never had a chance to really go into detail. So I thought that I will take this opportunity to say more about this. So let's see what is about here. So the topic is singular links, moreover, singular link cobordisms. And then similar to the Reidemeister moves or extended Reidemeister moves for singular links, there is Reidemeister type moves for singular link cobordisms. And if you impose a height function in the in R3, where you look at the projection of a singular link cobordism, you can you get this movie parametrization of diagrams that represent a singular link cobordism. And then the question is, when I look at isotopic singular link cobordisms, what are the moves that take me from a diagram to another diagram when I look at those diagrams from a movie parametrization perspective? So that this is the goal of this work. And it is similar to the movie moves of Scott Carter and Masahiko Saito for classical knot or link cobordisms. Okay, here we go. Let's start first by defining a singular knot or a singular link. We can think about a singular knot as an immersion of disjoint union of circles in R3, where we have finitely many singularities that are all transverse double points. So those will be the singular crossings. But I will be thinking about those singular crossings as vertices, in particular rigid vertices. And then a singular knot is a rigid vertex embedding of a four-valent graph in R3. So let me be a bit more specific here. So we can think of a singular knot as starting with a four-valent graph and you embed it in R3, but you think about the vertices as being replaced by rigid disks, in the sense that each disk has, well, we have four strands meeting at the vertex, so each disk will have four strands attached to it, and there is a cyclic order of these strands. And this cyclic order is determined by the rigidity of the disk. And then when we have an isotopy of this type of embeddings, that isotopy must preserve the cyclic order of strands that meet at a disk or at a vertex. So that is the preferred representation or how I'm thinking of a singular knot in this research. Then we work with diagrams of singular knots, and the diagram of a singular knot is a generic projection of that singular knot into a plane. And it is well known that two diagrams represent isotopic singular knot, if and only if they differ by a finite sequence of the following moves. Now, singular knots are considered as a subset of classical knots are considered as a subset of a singular knot. So certainly then the classical Reidemeister moves are among the set of moves needed to describe isotopic singular knot diagrams. But besides the Reidemeister type 1, 2, and 3, and of course planar isotopy, we have moves that involve the vertices. So the move that I denoted by R4 allow us to slide a vertex over a strand or under a strand. And the move R5 is actually what tells us that we do work with rigid vertex embeddings of 4-valent graphs, meaning that here, when we have this twist near a vertex, we do not just untwist those two strands, but actually we twist this as a whole disk, if you wish, and then the other, this crossing is not, it's removed on the left-hand side, but appears on the right-hand side. Okay, I will collectively refer to these moves as the extended Reidemeister moves. In order to understand the work for the movie moves for cobordisms of singular links, it is important to understand how we get to these diagrams for singular links. So let's analyze the projection of an isotopy of singular knots and links. Okay. This type of diagrams will contain zero-dimensional singular sets. Those are classical crossings and vertices. And then as an isotopy of a singular knot happens, these zero-dimensional singular sets become a one-dimensional set. So they trace a one-dimensional set. So that is in the isotopy direction. And then the philosophy of this set of Reidemeister type moves for singular knot diagrams is to study, to understand the most critical points that result from those one-dimensional sets and transverse intersections. Now, it is important to note that the moves for singular knot diagrams do not correspond to critical points for the vertex set, because the vertex set of a diagram, because during an isotopy of a singular knot, the topology of the underlying graph remains unchanged. So when we say here, classifying or understanding the most critical points of the resulting one-dimensional set, we will not look at the resulting one-dimensional set coming from vertices, but only from crossings. Again, because the vertex set does not change, the topology does not change through an isotopy of singular knots. Okay, so we have critical points of type 1, and that will give us the Reidemeister 1 type move and the move that I denoted by R5. So these moves R1 and R5 correspond to critical points of the double point set. So the double point set here is represented in red, here and there. And what we have here is, we know the Reidemeister type 1 move R1 corresponds to a branch point right here. So here we have the move read either from top to bottom or from bottom to top. And when you project that, you get this diagram. And this is the double point set here that the crossing traces in the isotopy direction. And then we obtain a branch point. Then for the move R5, this one corresponds to an isolated singular point. I will refer to that as a crossing vertex point. That happens here. So let's see what happens during this move. So the isotopy either from top to bottom or bottom to top. When that isotopy happens, this vertex will trace a one-dimensional set, as you see it on the right side. and the double point will trace a two-dimensional set that is represented in red. So that is in red on the right-hand side. Let me now erase that. So an R5 move corresponds to this isolated singular point where an edge, which is a vertex cross an interval, intersect this arc that the double point set creates, which is again the crossing that I have there and the arc that it traces. Okay, so this is a critical point of type 1 that gives us the moves R1 and R5. Okay, critical point of type 2, Reidemeister type R2 is related to this type of critical points. During this move, what happens, we have a critical point of a double point set. So if we apply the isotopy from top to bottom, we see that this arc is created, and then we obtain in this direction from top to bottom, we have a maximum point on this set, or vice versa. If we read the isotopy from bottom to top, we have a minimum point of that set. Okay, so this is a critical point for the double point set, maximum or minimum critical point. Then we have transverse intersection. Those are of type 3. Okay, and the move R3 corresponds to an isolated triple point, which happens right there. During such a move R3, a crossing point, so let's say this crossing, a crossing point in the diagram traces a one-dimensional set. So look here, this is the path that that crossing will traverse. And this one-dimensional set will intersect transversely with a two-dimensional set in R2 cross an interval. Now that two-dimensional set is the arc of the diagram times the isotopy. Okay, so it's this sheet. Okay, so that is a transverse intersection between a one-dimensional set and a two-dimensional set in R3. And this is what a Reidemeister 3 type corresponds to, or precisely we have this isolated point as a transverse intersection. We'll refer to it as a triple point. And then we have another type of transverse intersection, still of R3, where this time the corresponding point, I will refer to that as a singular intersection point. It is similar to Reidemeister 3 type move, only that now we have a vertex that passes over or under an arc. So then in the isotopy direction, the vertex will trace a one-dimensional set, and then this arc will trace a two-dimensional set, which is that plane. And then we have a transverse intersection that happens right there that gives us the isolated point that I refer to it as a singular intersection point. Now, all of these moves, R1 through R5, exhaust the possibilities for critical points and transverse intersection in R3 when an isotopy between singular knot diagrams happen. And therefore, these 5 moves are sufficient to relate isotopic singular knot diagrams. Of course, we also, when we look at diagrams, it's not hard to see that those extended Reidemeister moves do represent singular knots that are isotopic, so that the other direction of the proof is the obvious one. This was the longer one, a bit more challenging, but this is how one can show that those moves are sufficient to relate two singular knot diagrams that represent isotopic singular knots. Okay, now, if we are interested in categorical or algebraic description of singular knots, then we may want to do, we need to do more. In particular, we need to impose a height function on the plane of the projection of a singular knot. And then we get more moves. Now, these moves do not affect the topology of the diagram. And here we have the moves that correspond to, or the additional extended Reidemeister moves with height function. Okay, and moves similar to those 2 and 3 here that have, instead of a maxima there, they have a minima, are not listed here because they can be obtained from these two that are listed, combined with the exchange of levels of distinct critical points. So we always want to list the minimum moves that are needed. The singularities that appear here are cups and fall lines that are traced out by the maximal and minimal points of the singular link diagrams. Now, the cancellation of a maxima and local max and local min correspond to a cusp singularity, as we see here, cusp singularity of fold lines. Then, moving an arc past a maximum or a minimum if you have the other type of diagrams. So an arc passing over a maximum point corresponds to a transverse intersection between the fold line and the double point arc. Now the double point arc here is the path that in the isotopy direction this crossing traverses. So we get that red arc, and the fold line is at a maximum point that this point traverses in the isotopy direction. So we have a transverse intersection in the plane between this double point set and the fold line. And similar behavior happens here when the classical crossing is replaced by a vertex. Again, we have a transverse intersection between an edge there and the fold line. Now, these cover all type of possible changes involving cusps and folds. And let me add here that then these additional moves, together with moves in which relative heights of distance critical points are interchanged, are sufficient to modify the height function on any singular link diagram. Okay, so those moves together, those additional 3 moves with their analogs for minima and the other type of crossing type here, together with the 5 extended Reidemeister moves, are all moves that are necessary to relate 2 singular link diagrams that represent isotopic singular links when we also impose a height function on the plane of the projection. So with this, hopefully are ready to do the same for cobordisms between singular knots. Okay, so we need to go over some definitions here. Two singular knots, we call them cobordant if they are related via singular knot isotopy, so the extended Reidemeister type moves, together with Morse modification. So we have birth circle or death of a circle and Seidel transformations. Okay, so that is our working definition of cobordant singular knots. And then the surface that connects two cobordant singular knots, we will call it a singular knot cobordism. And we are interested in studying singular knot cobordisms in for space up to isotopy relative to boundary. Okay, similar to when we study classical knots or singular knots or virtual knots, we work with diagrams. So the same here. We start with a singular node cobordism, but we study those diagrammatically by projecting them onto a three-dimensional space. And the diagram of a singular node cobordism is a projection of that from R4 into R3. In our work, we also fix a height function onto R3, similarly as we fixed a height function onto R2 when we studied in the previous slides, when we studied isotopic, when we studied diagrams representing isotopic singular link. I got it right. When we studied isotopic, when we studied diagrams of isotopic singular links. There we go. So we want also now to fix a height function on R3. Now, such a diagram in R3, so again, a diagram of a singular node cobordism can be cut by planes that are perpendicular to a fixed direction in R3. And when you do that, you obtain a movie description for a singular node cobordism. Now we can regard a movie of a singular node cobordism as a sequence of singular link diagrams. We can cut it in such a way that when you look at the movie, you actually see a sequence of singular link diagrams, and we will refer to this as stills. Let me stress here that we do not put a height function in each of the stills. If we do that, we would have more movie moves. But that was beyond the scope of my research. Okay, so the time direction in the movie, to clarify, is given by the height function. And if we restrict the movie to a small interval of time around the critical level, we see two stills in the movie that differ by an extended Reidemeister move or a Morse modification. Okay. That is what I have written there. Okay, so the purpose of this research is to find the moves for movies that describe isotopic singular node cobordisms. Just as singular nodes contain classical nodes as a subset, also singular node cobordisms include classical node cobordisms in force space. And thus, the moves that we obtain here must include all of the 15 Carter-Saito movie moves for classical node cobordisms. It should be noted that these moves, due to Carter and Saito, are extensions of the 7 moves by Roseman that were moves for diagrams of node cobordisms where a height function on R3 was not imposed. Okay, so here I will use the labeling of those movie moves as Dror Barnatan used. Okay, so let's go over them. And again, the first ones that we'll have here in the following slides are the Carter-Saito movie moves for knotted surfaces. And again, those are movie parametrizations of the Roseman moves for diagrams of classical node cobordisms. The moves listed here correspond to invertibility of the classical Reidemeister moves. So this one corresponds to invertibility of the R1 move, both of them. And because the R1 move is not symmetric, we have two moves, or the two sides of the R1 moves are not symmetric. So we have two movie moves that correspond to the Reidemeister 1 move. For Reidemeister 2, we'll have we have actually also here two moves. Yeah, sorry about that. And then one for Reidemeister 3 type move. Here, this means that when you look at this movie move on the left side, that describes a cobordism, which is isotopic to the cobordism on the right side. Now, on the right side, we see is the identity cobordism. So identity cobordism here, identity cobordism here, and also here, identity cobordism in all of those. Okay, so those are the first 5 moves. And then we have additional movie parametrizations. Let's see what happens here. These are a bit more complicated. Just a second. Let's see what happens here on the left-hand side. I see a twist, so I can at some point eliminate that through a Reidemeister 1 move. But I will do that at the end after I slide this twist under that strand. So I can do that through a Reidemeister 2 move. And then I apply a Reidemeister 3 move to slide this crossing under the strand. And then I apply another Reidemeister 2 move to now have the full twist on the other side of the strand. And now I can eliminate the twist via a Reidemeister 1 move. And that gives us a cobordism, or this is a movie parametrization of a cobordism, and we can read it from top to bottom or bottom to top. But that will give us, or that cobordism is isotopic to the following, where the only thing that we do is just applying a Reidemeister type 1 move, and then slide that strand up. Okay, so those 2 movies represent isotopic singular or classical, actually here, classical, not cobordisms. The following one corresponds to the so-called tetrahedral move or quadruple point move in Roseman's move. What happens here, focus on this crossing and then that crossing. We can grab that crossing and slide it over that strand. So now the crossing is here, and then we can slide it over that strand as well. And now the crossing is here. And next we take the crossing there that now is here, and then we can slide it under this strand. And then here is the crossing now. And then we can slide it one more time under the following strand. Okay, so that is a sequence of Reidemeister 3 type moves, and together this gives a parametrization of a cobordism. But we can start first with this crossing and then slide that under the first strand that we see there in the diagram. And then we slide it under the following strand, and now the crossing is here. And now we grab the crossing on the left. We are here in this diagram. And now we slide it under this strand, and the crossing appears here. And we slide it over the next strand as well, and now it is here. Now we see that this movie parametrization does describe a cobordism that is isotopic to the cobordism on the left side. Now, if we do impose, as we want here, a height function on the free space of the projection, then we obtain additional movie moves that describe isotopic cobordisms for classical knots. We are still within the classical knots frame here. Okay, so it's important also to know that these moves do not affect the topology of the projection of that cobordism in R3. And we have these additional moves. Okay, so from the move 6 to move 15 here. Let's see what happens, for instance, here. You start with this diagram, say we read it from top to bottom, but we can read it from bottom to top as well. So if we look at the left side, we introduce on this side of the vertical arc, we introduce a Reidemeister 2 move, and then we slide that vertical strand under the crossing on the right. Or we can apply a Reidemeister type to move on the right side of the strand. And then we slide the strand under the crossing on the left side now. So now these two movie parametrizations to describe isotopic cobordisms of classical knots. I will not go over all of them, but I encourage you to pause the video and see what happens at a certain movie here. Perhaps I will just look at the last one. So we have three parallel strands, and I can take the two on top and I can apply a Reidemeister type 2 move between the two on top. And now here in this region, I can apply a saddle move and I get a diagram. Or vice versa, starting with the same three parallel strands, I can take the two in the bottom and apply Reidemeister type 2 move there. And then I apply a saddle transformation between these two strands to get this diagram. So again, this movie parametrization and that movie parametrization give or describe isotopic cobordisms of classical knots. And then if we allow those vertices, we'll have additional moves. Okay. And here are additional moves for singular knot cobordisms. So let's see what happens here. I denoted this by the next label, movie move 16. So here we have a classical crossing and a singular crossing. And what we can do, we can apply the move R5. And that is what we have here. And we can undo that. So this corresponds to invertibility of the move R5. And this one corresponds to invertibility of the move R4 when we slide a vertex over or under a strand. And then we have additional movie moves here. Let's focus on the one labeled 19. So I have this vertex and I look at the strands on the left side and I can apply a Reidemeister type 2 move there. But then here in this local region, I can apply an extended Reidemeister move R5, the one with the twist, and I get this diagram. Similarly, instead of looking at the strands on the left, I can take those on the right. And then I can apply a Reidemeister type 2 move there. And then I can apply an R5 move in this local region. So again, this movie parametrization and that movie parametrization, read either from top to bottom or from bottom to top, they describe isotopic cobordisms between singular knots. Okay. And additional cobordism here, move 18 and move 20. And there are more. Okay, remember that messy tetrahedral move or quadruple point move? That is a parametrization of actually the move with that name by Rosman. Well, we have similar moves here when we have some crossings being replaced by vertices. So here then we have three similar moves because here I have four strands and I can have a vertex replacing a here before we had a classical crossing. So I have a vertex instead of a classical crossing when I work with those two strands, or I have, instead of that classical crossing, I will have a vertex here, and then that vertex here is a classical crossing. So then we have a similar move there. Or we have a, here I should look at, instead of that classical crossing, I will have a vertex and then the other classical crossings remain there. And I'm just replacing that vertex by a crossing here. So that gives me 1, 2, 3 additional movie moves that are pretty much similar, these three. Notice that I drew them horizontally versus vertically as before, so that I can fit them on this slide. Now, In all of those moves, I can actually have similar approach where I will take so let's focus on this move, for instance, and let's look at it from left to right. So I see here a vertex that I can slide it over this trend, and then the vertex appears there. And then, let me see what we are doing here. Then this crossing this vertex slides under this trend. And next, I'm taking, no, I have to start again. Scratch that and let's start over. We are looking at that vertex. So we take that vertex and slide it under this trend, and we are here. And now we take that same vertex and slide it under this trend. So now we are here. Okay, so what we did, we just took that vertex and that went under those two strands. And now we can take this vertex and now we do the same and slide it over those strands that are underneath, and we get to that diagram. So this is a movie parametrization of a certain cobordism of singular links, but instead of starting with that vertex, I can start instead with this vertex. So that is what the second movie parametrization does. So this trend, this vertex, you slide it over those two strands, and now the vertex is there. And now you take the second vertex and slide it under those two strands, and you get that diagram. Right. So those additional movie moves, together with the 15 moves due to Carter and Saito for the classical knots, give the theorem for the movie move theorem for singular knot cobordisms. So here it is. Two movie presentations represent isotopic singular knot cobordisms if and only if they are related to each other by a finite sequence of the moves for knotted surfaces, those 15 due to Carter and Saito, plus the 9 movie moves in the previous two slides, together with moves that I did not shown here that correspond to interchanges of levels where distant critical points happen. Now, when we did look at those 25 moves in total, so 15 plus 9 that correspond to those with vertices, that involve vertices, those 25 moves, we can see that they do represent isotopic singular knot cobordisms. But the hard part of the proof, similar to what we did for diagrams of singular knots, the hard part is to show that the proposed list of movie moves is sufficient to relate any diagrams that represent isotopic singular knot cobordisms. And for that, we'll have a similar approach as we did when we analyzed the extended Reidemeister type moves for singular knot diagrams. So we need to study the projection of an isotopy on a plane, isotopy of singular knot cobordisms. Now, the philosophy behind the movie moves is that they do correspond to the following singularity. So we have critical points of the multiple point strata where the isotopy direction provides a height function. We'll refer to those type of movie moves as type A. So they will correspond to critical points of multiple point strata. Other type of movie moves will correspond to transverse intersection in the force space, transverse intersection between two type of strata. And once we impose, which is what we want, we have a height function in the free space of our projection of a cobordism. We have additional moves. Those will not affect the topology of the diagram, and they will involve fold lines and cusps. So we will look at local type of changes in one higher dimension as an isotopy of a singular knot cobordism happens. And we need to make sure that the listed movie moves cover all of the possible critical behaviors in the A and B and C categories above. All right, so first let's see what is the singular strata for diagrams of singular knot cobordisms. The zero-dimensional singular points on a given diagram of a singular knot cobordism are the branch points coming from an R1 move and the crossing vertex points that are coming from an R5 move. Then we have additional zero-dimensional singular points. Those are the triple points that are coming from R3 moves, the Reidemeister 3 type moves, and the R4 moves that when you have a vertex that you can slide it under or over an arc in the diagram. And I refer to that singular point, zero-dimensional singular point, as singular intersection points. So those are the zero-dimensional singular points, these four type of singular points. But we also have one-dimensional singular sets in a diagram of a cobordism. So those are the double point arcs that a classical crossing traverses in the isotopy direction. And similarly, we have the one-dimensional set that every vertex traverses in the isotopy direction. So I will refer to that as the edge, an edge of a cobordism. So during an isotopy, the zero-dimensional singular points, the four that we saw in the previous page, they trace a one-dimensional set during the isotopy, and the one-dimensional sets will respectively traverse two-dimensional sets. Now, the topology of a cobordism is unchanged during an isotopy. So then the movie moves will not correspond to critical points for the edge set, because if we did have critical points for the edge set, so those a vertex cross an interval, that is an edge set. If there were critical points corresponding to the edge set, then the topology would be different for that cobordism. So when we look at the one-dimensional singular set in the diagram of a cobordism, we will only look at the double point arcs, those that were drawn in red. Okay. So we start classifying, we look at all of those categories A, B, C, when we get the movie moves, and we want to make sure when we cover all of them that we got the 25 movie moves that we listed in the theorem. Okay, so the movie move number 1 corresponds to a critical point of the branch point set. Now remember that a Reidemeister 1 move corresponds to a branch point. So here I have one Reidemeister move and another one. So we have two branch point sets. So this is one side of the movie move. This is another side. And here we have diagrams of those cobordisms drawn in, of course, R2. But when you look at the branch point in the isotopy direction, so you look at from this diagram to that diagram or vice versa, and those branch points traverse, we have this red arc actually in the cobordism. We have that red arc for the branch point set. But in the isotopy direction from left to right or right to left, something happens with that arc. And either these two branch points disappear in that direction or they appear, and we obtain a optimum, either a maximum or a minimum depending on the direction for the isotopy. So we have an optimum on the branch point set. If we look at the other movie, where I start with a twist and then untwist it and I twist again, what happens here? We have a saddle on the set of self-intersection. So the red curves, self-intersection of the diagram. Okay? So these are the critical points on the branch point set. So those related to Reidemeister-1 move. Next, another type of zero-dimensional critical point were the crossing vertex points. Those that are given by Reidemeister 5 or Reidemeister type 5 move, where we have that type of twist behavior. So when I apply this move, say from top to bottom, or this cobordism, when I read it from top to bottom, I have somewhere at the midpoint there, I obtain that singularity that is a crossing vertex point. And we obtain another one here. So then in this diagram, you will see that these 2 points, or these arcs, let me look at the points. These 2 points will either disappear if I go in that way, or they will appear. However, these 2 points, they get closer and closer together, and they traverse a one-dimensional set. And through the isotopy, that set will have a minimum or maximum. So this movie move corresponds to an optimum max or min, the critical point of the crossing vertex set. So in the isotopy direction, a non-degenerate critical point will correspond to annihilation, if I go that way, or creation of a pair of crossing vertex points. Okay, we have another type of zero-dimensional critical points. Here we have the triple point set that comes from a Reidemeister 3 type move. Okay, so here is that singular point that gives us a triple point. So we have here one of them because we have a Reidemeister 3 move, and then we have another one due to undoing that Reidemeister 3 move. And here we have the identity cobordism. So in the isotopy direction, these 2 pairs will disappear, or in the other direction, they will appear. Again, these 2 points then in the isotopy direction will get closer and closer together, and they will trace a one-dimensional set, and we'll have a maximum or minimum on that set. So this move corresponds to a critical point of the triple point set. Similar to the type 3 move, we have the move R4 that involves a vertex. So then this move, 17, will correspond to a critical point of a singular intersection point set. So this is a singular intersection point and another one, and then the one-dimensional set that these 2 points will traverse in the isotopy direction. I refer to it as a singular intersection point set. And then this move will correspond to a minimum or maximum in the isotopy direction. Or equivalently, in the isotopy direction, a non-degenerate critical point will correspond to the annihilation or creation of a pair of singular intersection points. Okay, so those were of type 1 move, when we have zero-dimensional critical points. We also have critical points of the double point set. Okay, so I refer to those as A2. And these correspond to the Rosman bubble or saddle moves. They are parametrization of those moves that Rosman referred to them as the bubble move and the saddle move. Okay, the double point set there, which happens due to the Reidemeister type 2 move, evolves to a surface during an isotopy. And the critical point of this surface for the first case will have max or min, so optima points, or saddles for the second case. They will correspond to the 2 movie moves here. Okay. Next, we have transverse intersections. So the next set of movie moves deal with transverse intersections in the 4-dimensional space. So remember here we are looking at 1 dimension higher. The projection of a cobordism is something in 3 space, it's a diagram in 3 space, but in isotopy direction, you have that projection times the isotopy, so you get something in 4-dimensional space. So we look at transverse intersections in the 4 space. So those will be between something that are 1-dimensional and 3-dimensional, and something between 2-dimensional sets. Okay, so we will classify them as of type 3.1 and as of type 2.2. Okay, starting with type 3.1 intersections first. The branch point passing through a transverse sheet is this type of intersection. So here we have the movie parametrization for the corresponding isotopic singular knot cobordisms, actually classical knot cobordism only here. And here are the corresponding diagrams. So let's see why this is can be described as a 3.1 transverse intersection. What happens here is that we have this crossing that passes under a strand. So this crossing here in the isotopy direction actually it's not a crossing, is the branch point that we get there that in the isotopy direction will transverse a 1-dimensional set. And then when you look at this strand in this cobordism gives us that 2-dimensional set, but in the isotopy direction that becomes 3-dimensional. So that is the 3-dimensional set that intersects transversely with the 1-dimensional set that gives us this type of transverse intersection. So again, this is a branch point passing through a transverse sheet. Next, we have a crossing vertex point passing through a transverse sheet again. Here we had the move corresponds to an isolated point that is created as the transverse intersection between a crossing vertex point set and the 3-dimensional set. So the crossing vertex point set is obtained when we apply, let me see here, crossing vertex point set is this point, which happens when I apply this twist move, the R5 move. So when I get from this steel to that steel, we'll get that crossing vertex point set. Okay. Now that crossing vertex point set in the isotopy direction becomes 1-dimensional. But also when you look at the move, you see that has to slide under that strand. So that strand there in the cobordism is given by this plane, this 2-dimensional set. And in the isotopy direction, either direction, that 2-dimensional set becomes 3-dimensional set. So this point in the isotopy direction becomes 1-dimensional and will intersect transversely with the 3-dimensional set that this plane will traverse through the isotopy. Okay. Other type of transverse intersections are corresponding to the tetrahedral move or quadruple point move of Rossmann. So this is the parametrization of that move. And what happens here is that the triple point, which is the one that, for instance, when I take this crossing and I slide it over the strand, at that moment, a triple point appears, but that triple point in the isotopy direction evolves, so it evolves in the space-time to become a 1-dimensional arc. And that will intersect transversely with a three-dimensional solid. Okay, and that will give us an isolated quadruple point. Okay. Similar transverse intersections we have when one of the classical crossings are replaced by a vertex, and that will give us three type of moves as we described before. So again, this is a 3-1 type transverse intersection. And we also have when instead of having one vertex and the classical crossing, I can have both of them as vertices. And this also becomes a transverse intersection, but now of 2-2 type intersection. I'm trying to see if I can quickly explain this. And while I'm looking for my words, let me look at the other bullet points. It turns out that the intersection between double point arcs can also be regarded as another way to interpret the movie move MM10, and the intersection between an edge and a double point arc. So let's see here. I was saying that I will try to explain this transverse intersection between sets, two-dimensional sets. Okay, let's look at one of the vertices. That vertex in this cobordism becomes an edge, but in the isotopy direction, that edge becomes something two-dimensional. And similarly for the other vertex. Becomes one-dimensional in this cobordism, but in the isotopy direction becomes something two-dimensional. So here, for instance, these two black arcs in the isotopy direction, they become two-dimensional. And the movie moves that I mentioned that can be also regarded as a 2-2 transverse intersection are these moves, because I can think in the same way. For instance, this black arc in the isotopy direction becomes two-dimensional, and then which one? This red arc becomes also two-dimensional in the isotopy direction. And similarly here, we can just focus on this red arc in the isotopy direction becomes two-dimensional, and then you can focus on that arc in the isotopy direction again becomes two-dimensional. So that's another way to interpret this 3-1 type transverse intersection, but only for those that give us a tetrahedral move, and these similar ones when you have a vertex. Okay. So the previous moves are those that do change the topology of the cobordism. Now we have other moves that do not change the topology of the cobordism, and we have them only when we impose a height function in the three-dimensional space where we project our cobordism. And the remaining isotopy moves then will involve fold lines and cusps. And those changes that involve cusps are listed here. And other type of moves are those that affect the relative position of double point arcs in relation to a maximum or minimum or saddle in a two-dimensional set, in a facet of a cobordism. So here in this move, what happens is that a branch point that appears due to a Reidemeister 1 move, so a branch point may pass through a maximum or minimum on a fold line, or a branch point passes through a saddle on a fold line. Similarly, we have a double point arc, a red arc that is created by a Reidemeister type move, Reidemeister type 2 move there. So a double point arc may pass over a maximum or a minimum on a fold line. And similarly, such a double point arc that appears from a Reidemeister type 2 move may pass through a saddle on a fold line. Continuing this type of classifications, there are other changes that affect the relative position of singular points in relation to the optimum point of a double point arc. Man, so many words there. Okay, so let's look at the diagrams there. We can have a triple point, which is a point that is created through a Reidemeister 3 type move, which you see here. When I look at this diagram from here to there, you see a Reidemeister type 3 move, and you see it here, the triple point. That can be pushed over an optimum point on a double point arc. The double point arc appears because of the Reidemeister type 2 move that we see it here. Okay, so triple point can pass over a maximum or minimum on a double point arc. We can also have a crossing vertex point. Stop there. So the crossing vertex point is the one that appears when we have that R5 move, the twist move. So that happens from this diagram to that diagram or vice versa. So here is the point in the projection. And then we also have a Reidemeister type 2 move that gives us that red arc. So here, this movie move corresponds to having a crossing vertex point that can pass through a maximum or minimum on a double point arc. Furthermore, we can have a singular intersection point, okay, that is obtained by taking a vertex and slide it under or over an arc. So that creates this point. And that can pass over an optimum on a double point arc, so over a max or min. And the double point arc appears here again because we apply a Reidemeister type 2 move. Okay, so this is another such movie move when we have it, which we have it only when we impose a height function on the projection of the diagram. Okay. All of the moves that we listed here, it turns out that they cover all of the possible critical behaviors in the categories A, B, C that we listed earlier. And thus, the list of our movie moves are sufficient to relate diagrams of isotopic singular link cobordisms. Now, in the movie moves that I showed here, those the moves in which distant critical points interchange the levels where they apply, they are not listed among the movie moves, but they are included in our movie move theorem. I am done. I just want to mention something that the set of movie moves can be shortened a bit. Just a second to get to those. It turns out that if you take the movie move 11 and 13, where do I have it? So if we take the movie move 11 combined with 13, one can obtain the movie move 12. And moreover, if we take the 111 with 15, one can show that we can recover movie move 14. That is due to a theorem first discovered by John Fisher. However, I included all of the movie moves to be consistent with what researchers have done recently, but also because I didn't actually know, I did not know about that theorem at the beginning when I started doing this research. So I think those were all of the slides that I had, and thank you so much.